So good afternoon, everyone, and thank you all for coming. It's so great to see a packed house here. We have a very exciting Dean's Distinguished Lecture for today, and very honored that we have the 2014 recipient of the Nobel Prize in Physiology or Medicine, so it's such an amazing treat. Before we get started with the lecture, I just want to thank the staff of the Center for the Neurobiology of Learning and Memory, Nan, Colette, and Lori Metarate for all the help that they have provided us in making this a success. And also, of course, the staff in the Dean's office, particularly Elisa and Andrea, Andy, Brian, and Benedict for making this such a wonderful event. Afterwards, I'd like to remind everyone that we'll have a nice reception just outside, so I hope you all can stay for that. And it's my job to introduce Professor Bruce McNaughton, who will introduce today's distinguished speaker. And I am very proud of the fact that one of my last tasks as chair of neurobiology and behavior was to recruit Bruce to UC Irvine. And we were able to recruit him as a distinguished professor, and he's one of three distinguished professors in the School of Biological Sciences. So it was a real coup for us to get him here. As some of you know, Bruce himself has been an amazing pioneer in understanding how large populations of neurons communicate. He's really pushed the frontier in technological developments, has an truly distinguished curriculum vitae, and has made outstanding contributions to the field, has won many, many awards. One of the most notable one is, of course, he was the first recipient of the Polaris Award, which I think is the largest award ever given out in Canada. It was something on the order of $20 million, and so Bruce was the recipient of that. So let's welcome Professor McNaughton.
Thank you very much, Frank. It's a pleasure to be here, and it's a great pleasure and an honor for me to introduce my very close friend, former mentor, and lifetime scientific sparring partner, John O'Keefe, who is going to give the Dean's lecture today. It's often said that chance favors the prepared mind. And in sometime around 1970, 69, John was at University College London, having recently got his Ph.D. at McGill University in Canada at Don Hebb's Department of Psychology. And he was just beginning to experiment with putting microelectrodes into the brains of conscious animals who were undergoing or doing some kind of behavior, and just exploring what it was that made neurons in the brain tick. He used to call it neuropsychiatry. He was poking around in a number of different parts of the brain, and eventually I think he put his electrodes in the hippocampus and discovered that there were cells there that, people had recorded from these cells and they couldn't figure out what was going on. And he watched, and in those days you listened on the audio monitor, you didn't collect data on a computer, and he said, goodness, these cells care about where the animal is. And from a scant data set which consisted of about 11 cells, if I remember correctly from the first paper with Ostrowski, he came up with the theory. Paper was called The Hippocampus as a Spatial Map, Preliminary Evidence from Unit Activity in the Freely Moving Rat. And he was mocked by many of his colleagues. I think it was maybe, well, over the course of the next 10 years, he and Lynn Nadell, who's at the University of Arizona, produced a landmark book called The Hippocampus as a Cognitive Map, which was fundamentally based on John's observation and covering all the literature, which then kind of suddenly came together into a picture of what this structure, which previously had been thought to be part of the olfactory system, was actually engaged in. So I think this discovery came about because John had been interested in space. He'd read Kant and the philosophers, and also some of the earlier behavioral studies on spatial mapping. So he knew what it was when he saw it, and I knew that sooner or later, if I stuck to his coattails, I would be giving this introduction to a Nobel Prize laureate. I'm not going to list all the awards that John has received because they're in your handout, and besides which I would take up too much of his time. So I would just like to welcome John and thank you for this opportunity.
Well, thank you very much, Professors LaFerla and McNaughton, for this kind invitation. It's an honor and a privilege to be here to address you. And thank you very much, Bruce, for that, that very kind introduction. And it certainly is true that although Bruce and I are very good friends, more than half of the time we talk to each other, it ends up in a few words. So perhaps we could switch over. Yes. Okay. Thank you very much. So I want to do two things in this talk. I want to take you back to 1970 or thereabouts and give you some feeling, some flavor for what we thought about this brain region called the hippocampus or the hippocampal formation, and how we went about trying to understand what its function was. And then I'll take you through a very rapid history of some of the highlights of what we found out over the ensuing years. And I'll try to convince you that if I have one talent, and I probably have one talent, and that is I've been able over the years to actually attract extremely talented, creative people to my lab. And I have to say right from the get-go that at least half or more of what I'm giving the credit for is really due to them. So we'll have a gallop through the history of hippocampal studies, and then I'll hopefully after about a half an hour, I want to come to a much more nitty-gritty subject, which is a question that's been exercising the whole field for some time now, which is what these cells, the grid cells, are doing, and I'll tell you what they look like, and particularly whether they can, in fact, provide what we call the metric of the cognitive map. So that's the structure of the talk. Let's go back then to 1970 or so. And what we knew when we first became interested in the hippocampus is essentially shown in this slide. We knew that this area here, and it's shown in cross-section here, you can see this great big hole. Here's the structure here. And this great big hole represents the tissue that was removed from the brain of this man, Henry Mollison, who had severe epilepsy, and for which he was offered a frankly exploratory operation, which was the removal of a large part of tissue on both sides in the temporal lobes. And in fact, this operation had a reasonable, successful outcome in the sense that it reduced the number of seizures that he had, and it made his life a lot more bearable in terms of his day-to-day activities. Unfortunately, it became very, very clear right from the day after the operation that the cost of this, the price that he had to pay for this, was a profound amnesia. he lost a large part of his memory. He lost a large part of his ability to store new memories, and he lost quite a considerable number of the memories that he had stored before the operation. And over the years, Brenda Milner, who was the first one to report him, his case, and her student Sue Corkin, and many others have struggled with trying to define exactly what it is that HM or Henry Mollison, what his deficits are. And Sue Corkin has reviewed all of that literature and presented it in this really very nice book, which not only tells you about the formal psychological studies that have been done on HM, but also about a lot of anecdotes. You get a very clear feeling from the book as to what it's like to live your life without a past and without a future. He's locked in the eternal present. And over the years, both Milner and Corkin have come to conclude that he has lost not all memories, but a rather selective kind of memory. And that selective kind of memory is a memory for what we call episodic memories, episodic episodes. It's the ability to remember what you did in a particular place at a particular time. He has other kinds of memories. He remembers things about, he remembers facts, he remembers all sorts of things. He can do motor skills. And I've taken one quote from the book by Corkin, which I think summarizes what his loss is. He cannot recall anything that relied on personal experience, his day-to-day experience of the events of his life, such as a specific Christmas gift his father had given him. He retained only the gists of personally experienced events, plain facts, but no recollection of specific episodes. And that's I think, summarizes that there's a little bit of controversy. Some people like Larry Squire in California here have a few objections to that very simple characterization, but that gives you a flavor for what's wrong with HM. Now, when we, in 1970, decided we were going to look at the hippocampus, we decided to take a very different tack. Rather than looking at patients with damage to the hippocampus or otherwise, we decided that it might be nice to put electrodes into the structure and to see if we could see what the cells were interested in. And I have to admit, I expected that we would put the electrodes in, look at the cells, and train the animals on some simple memory tasks, and Bob's your uncle, that would be it. We'd know what memories look like at the cellular level. Life is not so easy. Here is the hippocampus shown in red here, and here is the structure shown in what's called a sagittal, parasagittal section, looking at the brain from the inside out. This is the temporal lobe, and you can see it has this worm-like configuration. And for a while, people wanted to call it the worm, and it was only eventually called the hippocampus or the seahorse because of its similarity to that. We didn't look in humans, we looked in animals, and specifically in the rat. This is a cartoon of the structure of the hippocampus itself, and also the surrounding areas, which were also, by and large, removed in HM. So our electrodes were placed into this area here, called the CA1 field. There are other CA fields here. We're not still sure exactly what the difference is between those two fields. They're defined anatomically. There's an area called the dentate, which I won't mention again, although it's an area dear to Bruce's heart. There are these areas behind or in back of the hippocampus proper called the subicular areas, the subiculum, presubiculum, parasubiculum. And finally, what's emerging as an extremely important area is a bit of cortex called the entorhinal cortex. And as I'll show you, many of the interesting spatial cells are found in the entorhinal cortex. Now, it turns out that all of these areas are densely interconnected anatomically. There's a very strong projection from the entorhinal cortex into the hippocampus, from the hippocampus into these spicular areas. We won't go into the anatomy very much, but I think you'll see the anatomy emerging from the functional descriptions of the cells when we get to them. Okay, so what did we see? Well, as Bruce has already mentioned, I expected to see that we would find memory cells. So we trained animals on very simple memory tasks. Go to this object to get reward, press this lever to get reinforcement. But we also looked at other things like what the animal was doing as it's part of his daily business, eating, drinking, sleeping, and so on and so forth. And to our surprise, and it really was a surprise, it took us a while to realize that it didn't make any difference to the cells what the animal was doing. It didn't make any difference what he was doing. It didn't make any difference why he was doing it, but the big correlate, the most important thing the cells were reporting on was where the animal was when he was doing the particular behavior. So it was on the basis of that that we started to think of the hippocampus has something to do with spatial mapping. Here's an example of the best of the cells. You can see the spikes here. That's what they look like if you looked at the oscilloscope. As Bruce said, in those days, we had virtually no way of actually permanently recording the cells except put them on tape. We would listen to the cells and we would watch them and try to see if we could see what the cell firing correlated with in the animal's behavior. You can see in this histogram here that the cell only fires when the animal goes to A and B. You get a lot of firing here. But when he's in other parts of this platform, and this is essentially a raised platform surrounded by curtains, you see that the cell doesn't fire at all. And in fact, most of these cells are silent. They're sitting there not saying a word. And until you find the right correlate, you sometimes would not even know that you had cells there. And sometimes you only know that when you look at the activity in sleep. And the cells tend to have a little bit more activity in sleep than they do otherwise. Well, on the basis of that, we concluded that these findings suggest that the hippocampus provides the rest of the brain with a spatial reference map. Now, we had only one cell, or a handful of cells. I think it was actually only 8. But each of them fired in a different location. So it was very clear that different cells preferred different locations in a given environment. Deprived of this map, the animal could not learn to go from where it happened to be in the environment to a particular place independently of any particular route, as in Tolman's experiments. And as Bruce said, I had essentially a misspent youth. I'm not a very good representative for the idea that people go to university, know what they want to do, take a course, go on, and so on and so forth. I wandered around for years taking philosophy courses, psychology courses. I spent years working for an engineering company making airplanes, and so on and so forth. So what I describe as a misspent youth, of course, actually put me in a rather good position to recognize that these cells might actually be representing something which most people were not willing to contemplate at the time. And of course, Tolman had been working away for many years up the road in Berkeley, trying to prove that rats, in fact, had some sort of a spatial representation in their brain. He looked at animals who were finding their way from one end of a maze to another. And unlike other psychologists who believed animals did that by running down to the first choice point, turning left, running to the next one, turning right, following essentially a route, he believed that they had a little representation, a map in their brain, and so that they could say to themselves, I'm over here and the goal is over there. I want to get there. How do I do it? And the system would generate different possible routes. So I knew about that. He had fallen into disrepute, whereas Jim will sort of correct me. Jim Agor was Tolman's last student. And by that time, I don't think he was taught, and his ideas were taught in many psychology departments. But I had read them as part of my misspent youth. So I was quite happy to entertain the fact that here what we had was the actual neural instantiation of Tolman's cognitive map. Okay, well, around this time, and as Bruce says, we wrote that very short paper, and everybody says, nah, that's crazy stuff. Go back to engineering, go back to making airplanes. So at this time, Lynn Nadell joined our lab, and here's Lynn. He's now in Arizona, so he was preparing for Arizona even when he was in London, wearing dark glasses. The two of us set out to write a very short review paper. We thought we could convince people of this idea if we showed them that it could explain a lot of the other things about the hippocampus, not so much the cells, but other things, like what happens when an animal has lost its hippocampus. And we started to write a very short review, and it took us about 7 years before we eventually published this book called Hippocampus as a Cognitive Map. And essentially what we were saying was that The hippocampus itself provides information about locations, such as A, B, C here. But in addition, that there probably were other cell types which were representing the relationships between place representations. It's not good enough to have just a place representation in order to have a map. You have to know the spatial relationships between the places. And one way you could do that is by having a set of vectors, AB, AC, CB, which actually represent the spatial relationships between them. So that was the basic idea. And it meant that, for example, if an animal was at A, and it knew it was at A, it had a pattern in its hippocampus which represented A, and it started running along vector AB, it would eventually get to B, and it would know it was at B just on the basis of the fact that it had been in a known place and then moved along a known vector. Importantly, it would also predict what it was going to find at B, so that if that didn't happen, and for example, somebody had changed something in the environment, you would have a mismatch signal which would enable the system to sort of update itself on the basis of mismatch. So we thought that this system was a cognitive system which actually learned about the environment on the basis of curiosity. Didn't learn about the environment because the animal was hungry or thirsty or something like that. It learned about it just because the hippocampus wanted to have a representation of every environment the animal ever went into. Equally important, if the animal wanted to go to B and tried to go along this path, and it was blocked, then it had the power, the system would have the power to do vector calculations, vector computation. So it would actually, for example, know that AC plus ACB would get it back to B as well. And so it was quite a speculative leap from what we knew. But we thought if this is correct, then we would expect several things to be discovered in the future. So we made very, very specific predictions. We predicted the existence of hippocampal signals coding for direction, distance, that's where you get your vectors from, and speed of movement. You needed speed of movement because you needed to offset the fact that animals could go from A to B running at different speeds. And the system had to know that it's running fast on one time and slow on another time to sort of get the system back to the right location. We also predicted that there would be a very small number of changes in the animal's behavior. And at that time, there were hundreds of experiments in which people had made damage to the hippocampus and found lots of different things. And it was pretty chaotic, I have to say. And we said, nope, there are only three things wrong with the animal. They can't learn about places, so they don't know when you plunk them down in A that they have been here before. They can't navigate because they don't have this system. And finally, they don't use exploration because they don't have this system which is curiosity-driven need to know what's there in the environment. Well, as I said, I think I have a little bit of a talent for spotting really good, creative people very early on. And the first one of these, in addition to Nadell, was Richard Morris. And he took it very seriously, the claim that animals with hippocampal damage would not be able to navigate in this very flexible way. And the idea is that if you block one route or put the animal in different locations, it can find its way to the goal by different paths. And so he went away and invented the Morris water maze, which is essentially a swimming pool for rats and mice. And the swimming pool consists of a tub with opaque water, cloudy water, so you can't see what's underneath the surface, with a platform that's hidden underneath the surface. So the only way that an animal knows where the platform is by looking around at the cues in the environment and triangulating and showing that that's where the platform is. And when you first put an animal down in this environment, he swims around, has no idea where the platform is. But very soon, within 8 trials, this is really one day's training, he knows how to go directly from any start to the platform. And when we made hippocampal lesions, what we found is that normals were, as I've just shown you, very good at doing this. Animals with cortical lesions were good, but the animals with hippocampal damage were totally hopeless at finding their way around from any start to any goal. So that was very encouraging. So we set out, and still at that time there were very few other people. There was a man called Dave Holton who was interested as well, and Jim Ronk in New York. But we set out to sort of begin to develop the technology for recording from these cells using a little bit more of an objective set of techniques than we had been using before, sitting there and looking and watching animals. And I'll just quickly show you this set of techniques, and I'll say a little bit more of this in the next slide. So here's the hippocampus, and we put our electrodes in here. We put a whole bunch of electrodes which we originally put single wires in, but then developed over the time into multiple wires, which enabled us to get a much better isolation. And I'll come back to this in a moment. And then we also developed techniques, computer-based techniques for recording from the animal's location using television cameras. And what you see I'll just show you one of our cartoons that was made by one of my colleagues. What you see if you do that, and you get an animal to wander around in a cylinder here, and he's looking essentially, he's actually not necessarily paying much attention to where he is. He's looking for where food is thrown in randomly into this thing. And you can see most of the time the cell just doesn't fire. But every once in a while, when he goes over to this area here, the cell begins to fire. And it doesn't matter if he's in this open environment, this open field environment, it doesn't matter whether he's moving northwards or southwards or east or west, the cell is quite happy to fire there. Now I'll show you in a moment that that's not true in every environment. And if you actually do a little bit of computation on it, you can represent the field by this heat map showing where the cell likes to fire and where it fires maximum, which is shown as this red color here, and that's the number of spikes per second. Well, as I say, I've been very, over the years, we've been able to we and other people in many other labs have been able to demonstrate that there are not only place cells in the hippocampus, but also several of the other cell types which we were really were very happy to see being reported because they fit into the sort of types of things that they carry the type of spatial information which is very important for producing cognitive maps. So in addition to the place cells, we know there are head direction cells which don't represent where the animal is, but the direction that the animal's head is facing. We know that there are grid cells which look like, at first pass, and I've already put a caveat down, they might be representing the metric of the map. And there are also boundary cells which seem to represent the distance that the animal is from big landmarks. So in a lot of the boxes we train the animal, they have walls on the boxes. And these cells seem to be telling the animal how far away it is from walls. Okay, well, a lot of this is due to technologies which we and many other people have developed over the years. As I say, I've been very good at attracting very talented people to the lab. And two of the very first people I attracted were Bruce McNaughton and Carol Bond. And they came around 1980. I had known them from their earlier time in Canada. And I had already decided that they were people to keep an eye on. So when they left Per Andersen's lab in Norway, I convinced them to come for a year to our lab and to learn a little bit of what we knew, but also, I have to admit, to actually give us a lot of a boost up in terms of technology. So Bruce already knew how to program computers, and he was terrific. And when I say we used tetrodes, that really was inspired by one of Bruce's original ideas. We were always having trouble with these electrodes that we used, single electrodes, in actually making sure we were recording from only one cell. We're sitting outside of a bunch of cells, and you see lots of spikes, as you could see in my original picture. And you were never quite sure, because you could see that sometimes you were mistaking two cells for one. And Bruce had a really great idea that maybe we should put in not one electrode, but two or more electrodes, and put them in very close together so that they would see the same group of cells. And this is the closest, I guess, I've ever heard to anybody having an aha or Leibniz thing. He was in the bath, apparently, when he had it. And so this simple idea that you could use as a kind of stereoscopic vision type of thing is really important. And over the years, his lab, our lab, and many other labs have developed these into not two, but four-pronged electrodes, which now everybody who does extracellular recording in 3D moving animals actually use this. Well, what do we do with them? Well, the first thing that we did was we tried to show the firing of these cells objectively. We tried to say, okay, can we demonstrate by using these overhead camera techniques that the cells only fire in one location? And we did a very simple task. This is an 8-arm maze, and the animal can only run from one place in the maze to another place. And those 8 arms are represented here. And you can see that the cell only fires through this histogram in this one location, in the south place here. And you can also show that by using a polar vector plot. Interestingly enough, and this is one of the first altercations between Bruce and myself, the cells only fired when the animal was running in one direction on the arm and not on the other direction. And I had come to believe, and it was very important, that these cells were place cells. They were identifying the location, but not, and they would do that independently of the way in which the animal moved or faced in the location. So that was a very important thing, and it's still the case that if animals are placed on mazes which narrowly restrict their ability to move, then they tend to fire in one location. We also showed that there was, in fact, a speed signal in the hippocampus. The cell firing rates increased as a function of how fast the animal was running. So the faster the animal runs, the higher the rate was. But it only occurred when the animal was in the right place. And more recently, we and others, particularly the Mosers, have been able to identify the main culprits in carrying the signal, which are speed cells. They find them mostly in the entorhinal cortex. They find cells which fire as a function of how fast the animal runs. And it doesn't make any difference whether he's running from one place to another or any other place. These are pure speed cells. They tell the animal how fast he's running, and they tell the hippocampus how fast he's running. Okay, so I'll take you through a few more things that we know about the hippocampus, and then we'll talk about the entorhinal grid cells. One of the things that I've already alluded to is that these cells probably can tell where the animal is on the basis of 2 different kinds of information. One is the fact that he's in a particular location means that he gets stimuli which are unique to that location. So the fact that I'm up here, I can tell from the relationship between the door and the screen and the lights where I am. So that's one obvious way in which place cells can locate the animal. But they can also do it, as I say, on the basis of an independent measure, which is once I know I'm here, I can locate myself in the next location by actually just monitoring how I move. If I move in a particular direction at a particular speed for a particular distance, then the system should do that as well. And over the years, the second system seems to work primarily on the basis of how far and in what direction the animal had moved in the interim. And some of these ideas, as I say, came from my misspent youth working on airplanes, which do, in fact, just that. They use information about speed and changes in angular velocity to compute where the animal is. Okay, well, over the years, I've tried to demonstrate this. It's bloody difficult in freely moving animals to demonstrate the difference between these 2 types of signals. So what we've been doing recently with Griffin Chen and John King is to train animals in virtual reality environments. Many, many years ago, in the mid-90s, Neil Burgess and myself and several others actually realized that virtual reality was a very good way to study spatial navigation in humans. And so we did some experiments in which we scanned people's brains while they were navigating through a virtual reality game. And over the years, Neil Burgess would say, why don't we do this with the animals? This would make life a lot easier if they would do it. And I said, no, I just don't believe it. That's a step too far. I don't believe that a rat or a mouse really would be able to take these stimuli in and understand that this represented an environment. I was wrong. And it turned out, it took until Harvey in David Tank's lab, following work on Holscher, actually showed that it was possible. And of course, the minute they showed it was possible, boy, did we very quickly jump on the whole thing. And so what you do is you actually create a virtual reality environment for rodents. So here's the mouse. And sitting on a styrofoam ball. The ball can rotate if the mouse runs on it. The animal's head is fixed, so it doesn't go anyplace. There's a little bit of a PC mouse here which measures the movement of the ball, so you know how fast and where the animal is going. And you present the environment on 2 video screens. And here's a screenshot showing what it looks like. It's an alley. We find it much easier to train animals to run down an alleyway than to get them to navigate in two-dimensional environments. But for a lot of the things we're interested in, that's going to be fine. You can see there are visual stimuli. That's the only stimuli he has. It's the only cues he has as to where he is, in addition to his own movements. And what we're going to try to do is see how important the visual stimuli are, how important the animal's own movements are, using our ability to dissociate these in visual. So this is the way we represent the environment. Here's the track. Here are a couple of visual stimuli at the sides and at the end. So let me just show you what it looks like. Here's from the animal's point of view. Here he's running down, and you hear a cell, which fires right in the middle of the track. And he's running down the track because he's going to get food reward at the end, a little bit of juice. And he runs again. He gets teleported back to the start, and that's what he does. He runs from one end to the other. And they don't seem to mind this rather strange thing. I thought they would have trouble. Strange thing where they get teleported from one place to another. Okay, so let me just briefly tell you what some of our results in this situation is. Well, we find place cells. We find cells which actually respond to particular locations on the track. Here's one of them. That's with all the cues present. If we take the cues away, the visual cues, then a lot of the cells, 80% of them, just stop firing. That doesn't mean they're all visual. It just means if we only give them vision, they can use it. But we're pretty sure now that if you give them other cues, other sensory information, olfactory and tactile, they can use that equally well. It turns out it's only the side cues which are really important. For most of the cells, they don't care about the cues they're running towards. They don't care about the cues they're running away from. They care about the cues on the side. And of course, if you think about it, rodents have this very, very wide peripheral vision, and they probably are spending most of their time looking out at the world that's out there rather than what's in front of them and what's behind. You can do the opposite of that. You can actually say, okay, we're not going to let you run down the track. What we're going to do is we're going to passively move you down the track. We drop the ball so that they can't actually move, and they sit there. And then you can see that about 25% of the cells are still capable of identifying the right location as the animals just passively move through the environment. We don't know whether that's because it's using the landmarks, that it says, okay, I'm now here because the visual cues are in this array, or whether there's a component of optic flow. As the animal moves through the environment, it sort of gives them some idea of how fast he's moving. We haven't done that yet, but we'll do those in daytime. So a really interesting experiment is to say, was that prediction that once an animal knows where it is in an environment and then can update the representation of its location by taking into account its own movements, can we test that prediction and can we actually show that it's correct? And the answer is yes. You can show that here's a cell that again fires about halfway down the track. If you get rid of all the visual cues, the cell says, don't know where I am. He just doesn't know. So he needs the visual information to be able to locate himself at the beginning of the run, at the very least. If you now do the following manipulation, you put him down at the beginning, show him all the cues, and then as he starts to run in this black area, you turn the cues off. So he has no visual information as he's running down the track. And you see that quite a few of the cells, half of them, actually continue to fire in the correct place. And we've also done other manipulations by changing the gain between how fast he's running and how far he goes in the environment, and show, in fact, that yes, the cells, many of them are relying mostly on vision, many of them are relying on both. They need to take into account the animal's own movements. And we're still trying to figure out exactly what the balance between those two are. Okay, I want to quickly run through a couple of the other cell types before we get to these this very interesting entorhinal cells, which we think might be providing the metric for the map. So some time ago, Neil Burgess and I, another very, very talented colleague, did an experiment in which we tried to see if we could stretch or manipulate the shape of the fields. So here's an animal that's been put into a square box, and we record the cell field here. Has a very nice field, as you can see. And then we put the animal into other shaped boxes. For example, there's a rectangle, which has about the same width here, but it's twice as long in that direction. We're essentially stretching the square. And we can stretch it in different directions. We can put them into boxes which are twice as large. What you see is that for some of the cells, the fields stretch in that direction, suggesting that the cell is really quite interested in how far the animal is from both of these boundaries. And as you begin to pull those boundaries apart, the cell actually stretches along that dimension to try to maintain a particular spatial relationship to the boundary. Well, I won't go into it very much, but as trying to understand that, we came up with a model, and we suggested that there might be cells feeding into the place cells, which looked very much, which looked very much like these abstract expressionist paintings by Barnett, Newman, and Rothko. And of course, what they're showing is that you can partition off a canvas with a large stripe that looks like this, either where the stripe is right up against the boundary or where the stripe is farther away from the boundary. And we suggested that there might be cells which do exactly like that. They are telling the animal how far it is away from particular boundaries. So here's just an example of one. This cell is actually telling the animal it's about, the maximum is about this far away from the boundary. If it gets farther away from the boundary, then the cell firing, as shown here, gets less and less. And if you put a couple of these cells together, you get rather respectable looking place cells. And you have to be careful of what you predict, because if you have these talented students, they go and look for them. Say, if you really believe those cells exist, then where are they and can I find them? And Cullen Lever went and found them not in the hippocampus, but in the subiculum, one of those areas just behind the hippocampus. And you can see these are what the cells look like. This one fires along the west wall. This is firing along the north wall. Some of them are small and hug up against the surface. Others are much larger. Some of them are away from the boundaries. So they fit all the descriptions of the model. And it's a very good example of making a prediction and holding your breath, and then having your students find those exact cells. And they don't care what environment the animal's in. He can be in a square box surrounded by curtains, and you get a nice field up against the west wall. You can be in an open tabletop circular, and you get a nice field up against the west wall. And they're not even particularly interested, as you can see from that, as to whether it's a wall or just an edge of the box. It's something about the boundary. So they're doing something really quite abstract. They're saying this is the boundary of the environment. And whatever creates the boundary, whether it's a ledge, a fall off, or a wall, they actually fire in that location. Okay, and you can take two of those and put them together, as I said, and make a very nice, respectable place. So that's one nice input to it. Another kind of cell that has been discovered by, in around 1984 by Jim Ronk is a head direction cell. And these are cells which actually tell not where the animal is located in the environment, but the direction in which the animal's head is pointing. And I won't say very much about these, except I'll give you a little bit of an example of what one of these cells looks like. They're found not in the hippocampus proper, but in this subicular area again, and also in this entorhinal cortex area. So every time the cell fires, we drop a couple of arrows here. And as you can see, the arrows are tending to point in this direction. Here is the summed representation of the arrows. Interestingly enough, if you record from several of these cells, they seem to be locked together. So if you find one which fires in the north in a particular environment, and then its fellow friends here firing, for example, in the northeast and the southeast, and you do some manipulation, change the environment, or turn the animal around, spin it around so it's dizzy, you find that they all rotate with exactly the same angle. So they seem to try to keep their internals angles relatively fixed relative to each other. So it looks as though this system is providing, essentially, a polar plot telling the animal what direction it is. So it's giving the directional information that one needs for the map. And then finally, and I'll spend the last, is it Frank? You're going to throw me off. In the last 10, 15 minutes, telling you about the grid cells. So around 1995, we were absolutely delighted and surprised that a couple of students who had come to my lab for a very short period of time, the Mosers, with their now students in Trondheim, discovered a type of cell which for all intents and purposes looks like it's providing a metric for the mapping system. And this is what cell firing fields look like. They don't fire in just one location, they fire in several locations. So they look like a bunch of place fields dotted around the environment. And if you look at it, they have this remarkable property where the fields are lined up in a hexagonal, here's a very good example, they're lined up at the ends of a symmetrical hexagonal structure. And so, and And if you put the animal back in the environment several times, you see that the firing pattern is exactly the same. If you record from different cells and different parts of this structure, the entorhinal cortex, what you find is that cells that are at the actual, and I have to say that Bruce McNaughton is involved in some of this. He had a long-term collaboration with the Moses. You find that different cells in different locations of the entorhinal cortex, either in the dorsal or the ventral part, have different spacings to the fields. So the fields seem to increase in spacing as you go from dorsal to ventral. And that spacing is quantized, as originally shown in our lab, but then shown much more extensively in the Moses lab. And it looks as though there are only 4 different sizes in any given animal for the spacing of these fields. You don't have a continuum. You can't move continuously from one spacing to another. You jump. There's a quantization of the signal. We don't know what it means. We don't even know what the actual relationship is. The Moses think it's about 1.44, i.e. the square root of 2 or so. We think that the jump is about 1.57, which is pi over 2. And we'll go into why that fits some of our ideas better than theirs. But the main thing is that these are quantized fields. So this is something totally unexpected in the nervous system. And you could take a couple of these grid cells with different spacings and actually put them together, just add them together essentially, and produce a very respectable place cell. Okay? So that's 2 ways in which you can produce place cells. And we don't know they're completely independent, but they certainly could be. Okay, I want to spend, as I say, the last 10 minutes or so telling you something more about the grid cells, but also putting a bit of a damper on certainly our enthusiasm, and I hope on your enthusiasm, for the idea that these are what some people have called the universal Cartesian map, the universal Cartesian grid structure for the map. And that's because they don't have all the properties that you would want that structure to show. Before I do that, though, I want to just show you something which is very intriguing, I think. And it's easiest to show it by this, on the basis of this painting by Roy Lichtenstein, who loves to cover all of his figures, his paintings. He's essentially a pop artist. He loves to cover all these paintings, whether they be landscapes or models of humans, with these Ben-Day dots. Okay, and these Ben-Day dots just happen to take a hexagonal symmetrical structure. And the thing about hexagons is you find them all over the world. You find them every place you look, you start seeing hexagons because it's one of the optimal packing solutions. It's a solution to optimal packing. Well, what I took away from this particular figure is if you look at these dots here, representing, let's imagine, a grid structure, and look at what he's done here. He's drawn a bunch of stripes, which then carry on and go up the curtain here. But he's drawn these stripes here, and you can see that essentially each one of these stripes lines up with one of these rows of dots. And if you can imagine then that stripes are one of the prototypical subcomponents of this grid pattern. And if you do things like take a couple of more stripes, for example, oriented at 60 degrees, here's one and here's another, and you add them all together, then you effectively can create this grid-like pattern, this pattern of grid dots on the basis of overlaying stripes. And we've gone into some ideas about how these stripes are created. I won't go into that now. It's based on some ideas about what the oscillations in the hippocampus are actually doing. What I will tell you is that Yulia Krupic in our lab actually has found a whole bunch of cells which look like they are subcomponents of these grid structures. They look like they're not entirely, but pretty close to the prototypical stripe patterns that you'd expect to be the components. So here are some grids, and here are some of these other cells. They're not grids. They're recorded in similar places, the paracebiculum and the entorhinal cortex. They're very, very stable. You can record them in several of them at the same time across trials. And some of them, as I say, show this very, very nice stripy pattern. They don't fulfill any of the criteria for being grids, There's a whole enterprise about how you characterize the grid-like structure of these grids and how you characterize their hexagonal symmetrical patterns. And so the grids get very high scores on this. These cells get very, very low or minus scores. So there are some of these cells which look like they are perhaps the components of grids, and these are stripes. Turns out that these stripy cells and other cells which are periodic, spatially periodic in the hippocampal formation, actually represent the majority of cells. So the grids are shown here. And here are the spatially periodic cells in general. They're a very large percentage of cells in the entorhinal cortex and the paracerviculum. They're much larger than non-periodic cells, so it seems to be a characteristic of the entorhinal cortex. But if you look at within this category of spatially periodic cells, you find that, in fact, the other cells, these stripy cells and other kinds of cells, are more abundant than the grid cells themselves. And they're not quite as stable if you try to look at the stability, because one of the things you need is stability. But they're pretty close to the stability of the grid cells. And some of them really do look like they're just pure stripes with a little bit of gaps here and there. Okay, so let me spend the last couple of minutes asking the question. We're getting a little bit too complacent. We think we have all of the components of the map, but science isn't like that. The more you look, the more you see things that you might not want to see. And that's what's happening with the grid cells, in my opinion. So here's another of Lichtenstein's paintings. It's called Yellow Cliffs. And again, here are these dots superimposed on this yellow cliff picture here, very much taken from some of his studies of Japanese paintings. And again, you can see that they show this grid structure. It's shown here, this very strong hexagonal symmetry. And you can imagine that this is a metric for the map. You can imagine that if you want to find how far up you've climbed up the mountain, you just count this row. If you want to find how far in you've gone, you just count this row. So they could, in principle, if you had the ability to read this representation, they could give you the metric for the map. Okay, well, if they're going to do that job, they have to do a few more things. They have to be repeatable. So you have to be able to come back the next day, and the grid structure has to be the same so that you get the same answer. They have to be internally consistent. So if you have a grid structure down here, and it tells you you've just moved 3 rat steps, it has to be the same up here. And philosophers have looked into this for many, many years. You can't have a measuring rule which is changing as you move around the environment. It has to stay the same, or else it won't work as a measuring rule. So the 3 rat steps down here have to get you a certain amount away up the grids, and 3 rat steps up here have to do the same. And then finally, they have to be resilient. They have to maintain their structure and not be changed by changes in the structure of the environment. You have to be able to tell that you're still gone 3 rat steps, even though you're now in a different box in a different location. And what I'm going to tell you in the last 5 minutes is that these 2 criteria are not actually honored by the grid cells, at least in some of the experiments which we've been doing. I'm going to skip this. And I'm going to skip, I'll just tell you a little bit about this. One of the things that Yulia Krupic and Marius have been noticing is that although the original idea behind the grids was that they were relatively independent of the structure of the environment, what box the animal was in, there are signs that they are paying attention to the structure of the environment. And the simplest sign is if you just rotate one of these square boxes, you find that the grid pattern rotates with it. We've known from the past that you could rotate a large object like a card, and that would rotate it. But this is a new finding. So if you rotate this pattern by 45 degrees, then in fact it rotates the grid structure in consonant with that. It doesn't do it if you rotate it by 90 degrees. So there's something about the actual structure of the box which is having a bigger influence on this grid pattern than we or the Moses or anybody else, I think, would have liked to believe. And I won't go into this too much, but if you look across a large number of boxes and a large number of grid cells, you find that the cells tend to have a particular orientation. The structure of the pattern has a particular orientation relative to the size of the box. They don't line up exactly parallel to it. They have an angle with respect to the size of the box. And you can see this is the same angle here. These are different cells, and here's again the same angle. So there was some feeling that these cells were obeying some rule about the relationship to the size of the box. And they only do this in squares. And you can see there are 3 lines here representing angles which are somewhere close to about 60 degrees. So they're close to the actual angle of the box, but not quite. And when we looked at it, we found that the difference from the edge of the box was about 8.8 degrees. The Moses have done a similar experiment. They find it's 7.5 degrees. And again, it's probably not a bad thing when we're at this stage in science that you get a difference of 1 degree or so between two labs doing very similar experiments. The thing for me which has the biggest influence on my thinking about the grids is what happens when Yulia and Marius record from grid cells which have very nice grid patterns in squares and put them in trapezoids. And it completely destroys the pattern of the grid structure. So whereas there's a very nice hexagonal symmetrical pattern here as shown in this autocorrelation here with these peaks all occurring in this very circular 6-fold pattern here. And you get this wonderful score, this grid score. When you put the same cell and let the animal run around the trapezoid, it completely destroys the grid structure. It seems to, as I'll show you in a second, seems to stretch it and bend it. And you can see here that it changes the ellipticity. It makes this pattern not circular but elliptical, and it seems to be stretching it out, and the grid measure just completely falls to pieces. So what's happening here? Well, what's happening is that the grid pattern in 2 halves of the square is very similar. If you do a correlation analysis, you see that it's very similar, whereas in the 2 halves of the trapezoid, it's very, very different. And essentially, the gridness is much, much worse in this part of the trapezoid shown here than it is in the trapezoid here. But even here, it's worse than it is in the square. And the other thing that's happening is the fields are getting bigger. So in one part of the trapezoid, the fields are bigger than they are in the other part. So the trapezoid, with its angled walls, is having a big, big effect on the structure of the grid, something that we really didn't expect before. And just to finish off, you can see here what's happening in this, again, lovely grid cell. What's happening is that as you move towards the nose of the trapezoid, the structure gets bent and it gets stretched. And it happens not equally to all components of this 3-component grid structure. It happens mostly to the components in this direction and in this direction. So we think that this makes it very unlikely that the grid pattern can represent a universal metric if it's going to be distorted by the shape of the box that you put the animal into. Now, there is a caveat. We don't know what the animal thinks about this environment. We assume that it's sitting there like we are, looking down from above and saying, yeah, come on, this is a trapezoid, and you should be able to tell the difference between these 2 locations as well as these 2. It may be that we're looking at a perceptual illusion. And one of the problems in this whole spatial field is that we haven't really been able to develop, and this is a criticism of ourselves, I think, we haven't been able to develop very good, powerful psychological tasks which tell us what's going on in the animal's mind. I used to talk about what's going on in the animal's mind in the 1970s and was laughed off the podium. We now talk about what's going on in the animal's mind, but we don't have very good tools for it. We don't know what the animal thinks this region of the trapezoid is the same as that region, and the distances are the same. So let me conclude then. So we think that place, head direction, grid, speed, boundary cells provide the components of a cognitive map. There may be other cells yet to discover. We probably don't need them. I think there are a lot of very, very intelligent, bright computational neuroscientists who are trying to come up with models, including some of the people who work with me. Bruce and his colleagues are doing the same thing. But there may be other things. There is always surprises, and you have to keep looking. Place fields can be identified by either landmarks or by path integration cues. It could be that the grid cells are part of a much larger set of cells which provide spatially periodic signals. And it may be that they're a particular subset. They're beautiful. We love them. but that you could do a lot of the work that they do using these other spatially periodic cells, which look like they're made up of one or two components of the grid cell. We don't know, and one of the things that Julia and people like that are doing is try to use Fourier spectral analysis to see whether we can come to some overall theory of all of these cells and make some sense of it. The grids may provide the metric of the map in some. They certainly could do it in a square, and they could do it in a circle, but not all environments, because it really is the case that the boundaries of the enclosure, the role of the boundaries has been underestimated. And the structure and the symmetry are permanently shaped by the geometry of the enclosures. And I didn't show you, but this is not some temporary effect of the fact that the animal might find it novel or something. This is true for weeks of recording. It looks as though this is a permanent effect of the effect of the trapezoid. And they can be non-homogeneous, so what happens in one part of the box doesn't necessarily happen in the other. So they cannot provide a universal metric unless you assume that the animal is having some sort of perceptual illusion in those boxes. These are the people I've showed you who've done the work. And these are the people who provided us with the money. And I just want to note the Gatsby Foundation and the Wellcome Trust, who've combined to provide us with a considerable amount of money to form the Sainsbury Wellcome Center. We've now built the building. We're fitting out some of the labs, and we're open for business. So keep your eyes, if any of you are interested in coming to London, keep your eyes on the nature and science. We're advertising at regular intervals. And thank you very much for your attention.